Hey everybody, we're going to look at cell potential, electrical work, and free energy, and I'll actually tie in a little bit of equilibrium in here as well. All right, so far we've looked at calculating the cell potential based on the two half cells that we have, and I've also showed you the connection between cell potential and the value of spontaneity, or the thermodynamic favorability of a reaction. And that's the connection to free energy. So I'm going to show you the actual mathematical connection today as opposed to just the arbitrary one. And the way I'm going to do that is through what's called electrical work. All right, so bear with me here. All right, so we want to perform some sort of work. We want to get some sort of energy out of the system. It's due to that EMF, or the cell potential. And remember that cell potential is measured in voltages, which is the joules per coulombic charge. Now the electrons are what have that coulombic charge. So if 1 coulomb of charge goes by, 1 kilojoule or 1 joule of energy or work is being performed. Okay, so keep that in mind, that coulomb is the amount of electrons, the charge of electrons going through the wire, and that's why it's intensive. It doesn't depend on how much you have, because if I were to double the voltage, or double the amount of electrons, then I double the energy as well, and it cancels out, and my voltage comes out the same. Hence why it's an intensive property and not extensive, and therefore I don't double the reactions as I saw when I was working with cell potentials. Anyway, everything's done from the work of the system, right? From the system's point of view. So the system is what is losing work, or energy in this case. So when a cell or battery produces a current, the cell potential has to be positive. We know that it's spontaneous, that it's going to perform that action. Well, the work has to be negative. So here's the equation. The equation for this is the coulombic charge and the energy. That's joules. Right here would be joules, and then we'd have work on the coulombic charge on the bottom. So Q, if you remember from physics, is the coulombic charge. So this would be our equation, just rewritten in different form with our variables, so our work, energy, and Q. All right, so don't worry too much about this. There's not much. I'm just kind of building up to the last slide here. All right. So if I rearrange that equation, what I'll have here is I'll have work is equal to the amount of cell potential coming from a cell or battery and the amount of coulombic charge that's going to transfer. Now the problem with this is the maximum energy that we could possibly get, and we're never going to achieve that. It's always going to fall short of that. So what happens is we can actually look at Q. We can break this down a little bit more and actually look at what Q is in general. Q is the quantity of charge in coulombs that's transferred. Now Michael Faraday found that 1 mole of electrons has a constant charge to it. So if I have 1 mole of electrons, Faraday found that the coulombic charge of 1 mole of electrons is 96,485 coulombs, or 96,500 coulombs per 1 mole. So for every mole of electrons, this is the charge that they have. That idea of a 1 is a relative charge for an electron. You could actually use this to figure out the exact charge of an electron by using, Avogadro's number and break it down to a single and figure out what the charge is for 1 electron. I'm not going to do that, but if you want, it might be fun. It's up to you. But anyway, the idea is that if we take Q and we want to figure out what the coulombic charge is, we need to know how many moles we have. And if I know how many moles we have, then I can use Faraday's constant to figure out the charge that I have. So I could take this information here and plug it back into this equation where Q is, and that's what I'm going to do on the next slide. Now, what the work is the amount of free energy that comes out of the system. If you remember in thermodynamics, the amount of heat or energy coming from a system that can do something for us is what we call free energy. So we can replace W max with the maximum amount of free energy that's coming from the system. So for galvanic cells, we get rid of the W, change it from work, and now bring it back to thermodynamics, set them equal to each other. Now we have Q. We're going to replace Q with N times Faraday's constant from the previous slide that you just saw, and boom, here you go. This is what you guys want right here. Under standard conditions, we can now connect free energy to the cell potential. And notice the negative sign in here. We've got the negative sign in here because if the cell potential is positive, meaning that the battery will run the way it's written, then the free energy should be negative and it will reverse the sign notation. This is the equation. So what this does is it allows us to measure a voltage in the laboratory, and then we could actually figure out what the free energy for that system would be. All right? And that would be your connection between cell potential and free energy. Now, you know that free energy is equal to, under standard conditions, negative RT ln of K. So since we know what the free energy is, if we just measure the voltage, we can figure out free energy, plug it into this equation here, and then figure out what K is. So we've got two ways to figure out, two things we can do with this cell potential once we find it. Figure out the free energy or figure out K. Anyway, so that's cell potential, free energy, and its connections to equilibrium. Now, let me just recap really quick here. Erase that. So if your cell potential, and I did this in one other video lesson we did before, cell potential is positive, free energy is going to be negative, and your K is going to be greater than 1. And that's true for any spontaneous or thermodynamically favorable process. These are the only three ways that you guys can figure out if a reaction is spontaneous. Cell potential, free energy, and K. Alright, so hopefully you can see the connections between all those, and I'll see you later.